All right. Hello, everyone, and welcome to the Green Bank Observatory's 65th anniversary colloquium series, where we will be exploring some of the great achievements made by the observatory since its formation back in 1957. And we'll explore how these topics continue to shape the field of astronomy. My name is Jessie Bublitz. I am a postdoctoral fellow here at the observatory. Now, over the course of this series, we'll hear from experts in various fields to which GBO telescopes and staff have made significant contributions over the years, and talking with us about both their history and the future role that the observatory will play. It is now my great pleasure to introduce the first speaker in our series, Dr. Karen Masters. Karen is currently a professor and chair of physics and astronomy at Haverford College, where she studies the structure of galaxies in order to better understand their history and evolution. She is the spokesperson for the recently concluded Sloan Digital Sky Survey 4 and the principal investigator for the citizen science project Galaxy Zoo, which asks the public to sort through and classify thousands of galaxy images, originally using SDSS data, and now with DECALS, the Dark Energy Camera Legacy Survey. Great acronym. Today, she'll be talking with us about the use of the 21 centimeter hydrogen 1 line, where back in 1977, R. Brent Tully and J. Richard Fisher published their study comparing the H1 line widths of galaxies using the 300-foot telescope, or as their paper refers to it, the 91-meter telescope, with their luminosities. And this relation has enabled estimation of the distances of these galaxies in what we now refer to as the Tully-Fisher relation. So let's please give a warm virtual welcome to Dr. Karen Masters. Karen, when you're ready, please take it away.
Thank you very much for the very nice introduction and the invitation. As people were joining, I was looking at the names, and it was nice to see a number of familiar names out there. So hello, I'm sorry that I wasn't able to come in person for this talk. It would have been nice to visit Green Bank, but luckily I'll be there in 2 weeks. I'm bringing a group of students in 2 weeks. So maybe I'll see some of you then. So I was invited to speak about observing galaxies at 21 centimeters using the Green Bank facilities. And so that is the brief I've taken. I'm going to be a little bit, I guess I'm becoming pedagogic here working at a liberal arts college. I'm going to speak a little bit about, what the 21 centimeter line is and why it's interesting in galaxies, not just for the Tully-Fisher relation, but for other applications also. I had some fun looking back at some of the early observations of 21 centimeter line from Green Bank facilities, mostly the 300-foot. So I'll show off some of that data from the early history of the observatory. And then I'm just going to blatantly skip a whole lot of effort and work and just talk about 2 of the large programs I've worked on or led using the 21 centimeter line to observe galaxies from Green Bank mostly, although a little bit of other facilities. This was a fun talk for me. I often, as you might guess from the introduction, I often talk more about optical galaxies, Galaxy Zoo, galaxy morphology, but my background back from my PhD was as a 21 centimeter observer, and so it was fun to come back and write a talk all about the 21 centimeter line and radio astronomy in general. Okay, so just to make sure we're on the same page, right? So the 21 centimeter line is a line that's created by the ground state of neutral hydrogen. It was predicted back in 1944, so before Green Bank was built. Hydrogen's beautifully simple atom. If the spin of the proton and electron are aligned versus anti-aligned, you have a little bit of an energy split that corresponds to the energy that a photon at 21 centimeters carries. And so if those atoms are excited out there in space, they will spontaneously flip and emit these photons. It's a highly forbidden line. The lifetime of a single atom is 10 million years. So this is not observed in laboratories on Earth, but because so much of the universe is hydrogen, so over almost 3/4 of the baryons in the universe are atomic or hydrogen, we just see it all over the place from out there in space. So it was first observed in 1951, detected in our own galaxy. And then in 1954 was the first detection from an external galaxy, in that case, the Large and Small Magellanic Clouds. Both of those observations predate Green Bank, which was established just a few years later. The earliest H1 observation I found published from Green Bank, there may be earlier ones that I missed because I will admit that I had limited time for my historical studies here. I did find one published in 1962 from Green Bank. But before we get there, let's talk about why people interested in galaxies are interested in the 21 centimeter line and emission from it. Well, primarily because as a field, we're interested in how galaxies get to be the way they are. Sometimes we approach that morphologically, asking galaxy zoo users to classify galaxies, and we wonder how they get the morphologies. But those morphologies are traced by stars, right? The optical light we see from galaxies is stars, and you can't make stars without the raw material to make stars, which is the cold gas that we trace using the 21 centimeter line and other methods for other phases of cold gas. In addition to needing cold gas, you need that fuel for star formation. You also need the right conditions for star formation to occur in the cold gas. The atomic hydrogen that's out there floating around in galaxies is just one phase of this gas cycle that we have going on in the interstellar medium in galaxies all over the place, where atoms of hydrogen cool and condense into molecular hydrogen, from which you form stars, and then the stars will then eject material that goes back into the interstellar medium. So again, just a review here, a reminder of the phases of cold gas in a galaxy. I'm going to be talking about the neutral hydrogen, the historically called H1 regions. The typical density is about an atom per centimeter cubed, and it's fairly cold, on the order of tens to hundreds of Kelvin. This is the thing that's emitting the 21 centimeter line. And in our galaxy, it's distributed in many galaxies, it's distributed in a flat, thinnish disk. In our galaxy, this extends over a wide range of radii, and the height is given there. It's relatively thin with a bit of a flare at large radius. I'm just going to contrast that to molecular hydrogen, which is, of course, the other phase of hydrogen, which we trace using radio waves. The typical density of a molecular cloud is 100 to 1,000,000 times greater density than atomic hydrogen. It's colder, it cools as it collapses. And in our galaxy, we typically find it in the inner part of the galaxy. It's a much smaller region in radius and much thinner. Hydrogen itself doesn't create emission lines, but we trace it via carbon monoxide, which has known correlations with the content, and that creates a radio emission line. So you probably remember this, but actually, as I was putting this talk together, I was struck by how important this is actually, how much of what we know about our own galaxy comes from 21 centimeter line of observations. So this rotation curve here is one that I use in teaching about rotation curves in galaxies. This is published in Clemens 1985, but you'll notice a lot of these points on the rotation curve of our own galaxy are coming from H1 observations, particularly inside the solar radius. And indeed, the early information we had about the structure of our own galaxy was coming from H1 observations. You can also do this with CO. But I found this beautiful diagram from a paper published by Oort in 1958. So again, not Green Bank data here, but showing the distribution of the color, the grayscale there shows the density of atomic hydrogen in the plane of the galaxy, where we're observing it from this location where the sun is. This is the galactic center. So this is the bit we can't see because it's behind the galactic center. And you do these sort of scans in longitude to map the galaxy. This is the kind of data that map and the rotation curve would be coming from. This example comes from the Leiden Dwingblue Observatory. I didn't find a single nice image from this survey, but there's a survey that was performed in the 1970s called the Maryland Green Bank 21 centimeter line survey. I imagine there were others too, but this one I found, which was fun, talking about making these kinds of observations using the newly resurfaced 300-foot telescope in the 1970s. So that's fun. I'll often talk about this kind of observations in teaching, and indeed I have done these kind of observations using a Green Bank facility, and I'll show you those data in a minute. But the idea is this, as you may or may not remember from a galactic astronomy class, if you look as an observer on the sun along a sight line in the galactic plane, if you're looking in the 21 centimeter line, you're going to be sensitive to blobs of 21 centimeter gas at a wide range of radii around the galaxy, all along this sight line. And as you see where they intersect the dashed lines, these blobs are all at different radius. A little bit of geometry and vectors will convince you that if you do this, the redshift of the blob that is at this tangent point, so the blob where the angle from the galactic center to the blob and then onto the sun is 90 degrees, that has to have the largest recessional velocity relative to the sun. And so you can make these observations and you spread out where you find this 21 centimeter line is spread out by the Doppler shift. And you can identify the largest redshift and say, aha, that's the blob that's at the tangent point. Geometry then tells you the distance that it has from the galactic center. And you've measured its velocity. And so you can use that data to put together a rotation curve. So I've visited Green Bank with students, and that's why I'm going to be there in a couple of weeks. And we make use of the 40-foot transit telescope. This is actually a very bad photograph of some data that was taken in our fall 2019 visit, when this group of students, Nick, Justin, Sydney, and Emily, were highly dedicated, spent most of the night observing at every 20-minute intervals to get different longitudes going over the top of the transit telescope, and put together this rotation curve, which you'll notice doesn't look quite right. I think there was a little bit of an issue with some of the velocity frame corrections that impact the low radius. But conceptually it was there, and they did a beautiful job getting the observations. We've also done it with the 20 meter, which you can access remotely. And so I use this quite a lot in teaching through the Skynet facility. So in 2020, we obviously couldn't visit in person, but the same class did this experiment making use of 20 meter data, and actually I think did a really nice job analyzing their data and getting a rotation curve. That's kind of fun. Okay, anyway, back to the research science. Let's talk a bit about neutral hydrogen in external galaxies, illustrated with this beautiful image of the Triangulum galaxy, the optical and 21 centimeter line, and then the 21 centimeter line color-coded by its Doppler shift. Some things that you should remember about the 21 centimeter or neutral hydrogen in external galaxies is typically about twice as extended as stars. That means it traces the potential well to large radii. So it's really useful for measurements which get at the dynamics or the dynamical mass of the galaxy. That's why its use in the Tully-Fisher relation is so ubiquitous. But also being out there at large radius, it can be the first component of the galaxy that's impacted by environment. So information about the neutral hydrogen also can tell you a lot about environmental processes impacting galaxies. We talked about this, right? So we've got our atomic hydrogen turning into molecular hydrogen, turning into stars. And so one of the things sort of remember about atomic hydrogen is it's pretty common that there's not as much atomic hydrogen right in the center of a galaxy, perhaps filled in by molecular hydrogen. If the atomic hydrogen gets to too high of a density, it turns into molecular hydrogen. This is very hand wavy, but near enough. And if it's at too low of a density, you can't detect it with a radio telescope. That means very usefully, even if you don't actually have an image of where the H1 is in a galaxy, you pretty much know the radius that it reaches to from its mass, because there's this really, because the density is basically, very constant. You get this nice relationship between radius and mass in H1, in neutral hydrogen. And then other things, the content, the H1 content of a galaxy correlates with things like star formation history and the types of galaxies. And I've jumped into this a few times, but we get it because it's an emission line. Even if you don't want the dynamics, you get it for free because you just get the Doppler shift. So we can look at some really nice images of the 21 centimeter H1 distribution in some nearby galaxies. So this is the M81 group. It's a classic image, right? Which we like to look at really because the optical view here, these look that, related galaxies, but they're not so clearly connected and environmentally interacting as we see them in the 21 centimeter image. And surveys like Things using the VLA have done 21 centimeter line imaging of a bunch of galaxies. And I just think this is a beautiful data visualization. These galaxies are all placed at the same physical scale. So you get a sense of the scale and sizes that you see in galaxies. And the one in the middle here is the Milky Way, an artist's impression, and then that data that I showed you earlier. So using Green Bank facilities is a little bit different, right? We don't have an array at Green Bank that we use to map 21 centimeter line. We're doing single dish observations of neutral hydrogen. And so here is a beautiful image of the Pinwheel galaxy that was taken by an amateur astronomer. And I'm just going to say, as a caveat, I'm using this for illustration. This is not actually the right scale. I think M101 is quite big in angular scale on the sky. But just don't worry about the numbers here. I'm going to use this as an illustration of the kind of data we get from single dish H1 for typical galaxies that we actually observe. If we observe a typical galaxy, a typical Sloan main galaxy sample galaxy with the Green Bank telescope, the beam or the area of the sky at which the telescope is sensitive to H1 is much, much larger than the optical galaxy. And we get a single pixel image or a spectrum of 1 pixel of this galaxy. Typical galaxies, say in the MaNGA survey, which I'm going to talk about, are a few tens of arc seconds across, whereas the beam or the region of the sky that the Green Bank telescope, 100-meter telescope, is sensitive to at 21 centimeters is 9 arc minutes. So it's much, much larger in scale. So we don't get images of galaxies, we get spectra, but spectra are useful. That said, some of the very early observations of external galaxies from Green Bank telescopes were of some of the really nearby external galaxies. So for example, the Andromeda galaxy, which spans several degrees across the sky. Here's some data that I found published in a 1963 IAU proceedings, where the Green Bank, the 300-foot, was used to map the rotation across the major axis of the Andromeda galaxy. So this was really neat. I think I sort of knew that the classic illustration we have of dark matter in galaxies, you know, M31 with the rotation going out to large radius, I definitely knew that was H1, but I don't think I knew that it was a Green Bank measurement of H1, demonstrating that there must be material in galaxies outside of the optical radius. So that was neat. The Triangulum galaxy is also pretty big on the sky, and so Green Bank has been used to make a map of the Triangulum galaxy. So this is that map that was published in 1970s. Even somewhat more distant galaxies. So this was a fun one that I found. So Mort Roberts did some observing with the 300-foot in the 1960s here, and at this time he's finding the highest redshift detection in 21 centimeters coming from Green Bank. So this is at 1,577 kilometers per second was the highest redshift. This is a 4x4 arc-minute optical view from SDSS of the galaxy. Here's the spectrum that was published in the paper and a little map. And if you look at the scale, here we're talking about a 10 arc-minute beam. And so the 4x4 arc-minutes is down here in the center. So this is not exactly a resolved image, but at least showing that the H1 is much more extended than the optical image, which is cool. It was fun to find this because I've observed maybe a little bit closer galaxies with a little bit of a smaller telescope at Green Bank. So another student experiment that we quite commonly do in one of my classes is use the 20-meter, again, remotely via the Skynet interface, to observe nearby galaxies at 21 centimeter lines. So this is a spectrum of the Andromeda galaxy taken with the 20-meter, the 2 polarizations of the 2 colors. This is what you get through the kind of online interface to Skynet. Students then download this data and do some processing in Python. So they're learning a bit of Python data analysis. And here's an example that August Muller, who's a current senior here at Haverford, worked on last year in the class. So here is her baseline subtracted 21 centimeter line profile of NGC 5055. And they can do a bunch of different calculations using these data, which they take themselves, which is fun. We get estimates of stellar mass from the literature, as well as an estimate of a redshift independent distance. And then as a class, we put the measured redshifts from the class along with the literature distances and also calculate the Hubble constant as a class. That's pretty fun to think that we're on the same sort of redshift scale as the state of the art in 1965, using the 20-meter for teaching. Didn't quite get out to the redshift of the one I just showed, but not too far off. Okay, so my final historical data set was this one. I found this from Mort Roberts, published in 1978. So it's a collection of 500 galaxies observed at the 21 centimeter, observed using the 300-foot telescope at 21 centimeter. And he talks about homogenizing the data. I sort of gave up after this point because it becomes harder and harder to identify which telescope is used. It becomes more common for people to use data from multiple telescopes and kind of pull them together. And there's just this sort of explosion of 21 centimeter line observations that happened in the 80s and 90s and 2000s as people were doing all this Tully-Fisher work that I'm basically going to mostly skip over in the talk. So I'm going to sort of segue into things I've worked on with the 21 centimeter Green Bank at this point. So one of the fun things about finding all of these observations by Mort Roberts when I was doing this digging was that Mort Roberts is the PhD supervisor of my PhD supervisor. So he's sort of there in my academic heritage. And when I finished my PhD working with Martha Haynes at Cornell, my PhD was on Tully-Fisher relation, mostly using Arecibo observations actually. But I moved into a postdoc job with John Herkra at the CFA at that point. So this is in 2005. And John had been working on this thing called the 2-mass redshift survey. So this was making use of the 2-mass survey, which had 2 identical infrared telescopes, one in the north, one in the south, and did a very homogeneous all sky survey in the near infrared. So J, H, and K band, but not the radio K band, the near infrared K band. And John had this idea. So the reason for doing this nice homogeneous all sky map is that then you get information about the local universe. And in particular, the distribution of mass in the local universe. If you're missing mass in a certain direction, you're going to get misinformation about the gravitational attraction that's felt by our galaxy, for example, from the lumpy material near us. And John was very interested in tracing the sort of a complete view of the map of the local universe, as well as tracing this gravitational acceleration caused by the lumpiness that we see out there. And so this was the redshift survey, the 2-mass redshift survey was published in 2012, following John's untimely death. And this was sort of the all sky view that we get from the redshift survey, where you can see all these beautiful different structures in the local universe. So John hired me on as a postdoc in 2005, basically to work on developing a matching Tully-Fisher survey that matched this 2-mass redshift survey. So we took our source list from the redshift survey. So we knew the redshifts of the galaxies a priori. We had this, the near infrared correlates reasonably well with stellar mass in nearby galaxies. So we had beautiful measurements of the mass, the stellar mass of the galaxies. And near infrared, the other benefit is you make the plane or the part of the extragalactic sky you cannot see because our galaxy is in the way. It's much larger in optical and narrower in infrared. So we got this, the idea was to have this beautiful uniform sky coverage. So if we want to do Tully-Fisher relation for these galaxies, we need line widths, rotation widths for as many of these as we can get. So this is a very noisy plot, which I made as a postdoc, showing the sky distribution of how you can get line widths for these different kinds of galaxies. Even back in 2005, Arecibo was doing the alfalfa surveys, or was starting the alfalfa surveys. But of course, Arecibo, when it was working, couldn't see outside of the sort of equatorial band. Alfalfa mapped most of it with an untargeted survey. So galaxies inside these yellow boxes all have 21 centimeter line observations that come from the untargeted alfalfa survey. But you see there's a huge amount of the northern sky that is inaccessible to Arecibo, or was chosen not to be observed by Arecibo because it's close to the galactic plane. And so we filled in this region, or we proposed to fill in this region by observing a selection of 2-mass galaxies with the Green Bank telescope. And then we had to do the southernmost stuff, even Green Bank can't reach. So we also got to go to Parkes and do some observing there. So this proposal was accepted, and we got telescope time starting in February of 2006. So this was actually a picture from my very first visit to Green Bank up by the L-band receiver, the 21 centimeter receiver on the secondary platform of the GBT. I don't know if any of you were around in Green Bank in February 2006. At the time, I was famous for being the observer who hurt their knee while skiing. And I spent about 2 weeks at Green Bank limping around, learning how to observe with the telescope. And the remainder of the 460 or so hours that we got for this project, the observations were done remotely from my office at Harvard. Oh yes, the other memorable thing about that visit was that there was a massive snowstorm, and so we went and had this beautiful walk out to the Green Bank telescope and got to take a picture of it in this beautiful snow stove position when the snow is falling off the telescope. So overall, observed almost 1,200 galaxies with Green Bank as part of this survey. It took a little bit of a while to get this published, but we did publish it in 2014. That was the data release paper for the Green Bank observing. Between the observations in 2014, I moved to Portsmouth and started working with the Sloan Digital Sky Survey and Galaxy Zoo, and also had 2 children. So hopefully you'll forgive me for the delay in publication, but it did get published and we published all of these data. And the Australian collaborators also have done quite a lot of additional work with the survey. So this is the list of publications out of that survey. So the first couple are to do with the observations. So we recalibrated the Tully-Fisher relation. This is presenting the observations from Parkes and the observations from Green Bank. And then Australian collaborators making the kinds of measurements that the survey was initiated to do. So this was the sky distribution of the final 2-mass Tully-Fisher relation that was used to derive the direction that the Milky Way is moving with respect to all of those galaxies, as well as the amplitude at which it's moving. So this is a component of the motion that we have within the CMB dipole. And so it's another tracer of cosmological parameters. And it's interesting. So that the measurements here, the lines here are lambda CDM predictions. And the measurements here are the measurements from the 2MTF survey. So as I said, meanwhile, I'd gotten more involved in the Sloan Digital Sky Survey. So since I was assuming this is mostly a radio audience, just a reminder about what the Sloan Digital Sky Survey is. It's a very large scale international project that does optical spectroscopy and optical imaging of the sky. So the first phase was the imaging, and then since I think about 2008, it's been entirely optical spectroscopy. There's many different sub-projects in the Sloan Digital Sky Survey. So in the introduction, it was mentioned that I was the spokesperson of the 4th phase, and the 4th phase had 3 different sub-surveys, and so there's a lot of different names and acronyms you can come across. Sloan also facilitates public data releases, regular public data releases with accessible data. So the sub-survey of Sloan 4 that I was most scientifically interested in was this thing called MaNGA. And as you can see from the title there, I'm going to tell you about the H1 follow-up that we did for the MaNGA survey, which turned into a very large program at Green Bank. So let's start though with what MaNGA is. So MaNGA is optical spectroscopy of very nearby galaxies. So the original Galaxy Zoo sample was based on SDSS images of 1 million galaxies. And those 1 million galaxies were special because they were the 1 million galaxies that had optical redshifts or optical spectroscopy taken with the Sloan telescope. And this is a picture of the Sloan telescope, by the way. For nearby galaxies, though, that single fiber, the region of the galaxy that Sloan measured a spectrum from was quite small compared to the angular scale of the galaxy. And so this is not actually a Sloan image of a galaxy. This is a Hubble Space Telescope image of a galaxy. And for illustration, I've put a little circle, the sort of typical region that for a very nearby galaxy in the Sloan sample, the kind where we see structures and the kind that ended up in the MaNGA sample, that's where the original Sloan spectra was taken. MaNGA decided it would be interesting to, instead of putting a single fiber, put an array of fibers. So this ends up being actually a little bit like a 21 centimeter data cube, the kind of thing you get from the VLA, where you have an axis that is spectra and then 2 axes, which are spatial directions. So in the optical world, this gets called an IFU survey, sometimes IFS for integral field unit or integral field spectrograph. And the MaNGA observations happened during the 4th phase of Sloan, which so they ran between 2014 and 2021. And overall, 10,000 galaxies have this kind of measurement made for them in the MaNGA survey. There's some other similar surveys. There was one that ran in Australia called SAMI that did 3,000 galaxies. There's one called Khalifa, which has on the order of 1,000 galaxies. But MaNGA is the biggest with 10,000 galaxies of this kind of data. So I mentioned I was talking about spectra and fibers in the MaNGA survey. So the way the Sloan survey works is it measured multiple optical spectra at once by plugging optical fibers into these plug plates. MaNGA developed this sort of it's called a ferrule, this little piece of metal into which you could feed multiple fibers to make this little hexagonal array of circular fibers. And then those get plugged into the plug plate, and we actually can do 17 of those at once with the MaNGA instrument. It's using the same spectrograph as the Sloan surveys use, so very similar optical spectra. But instead of a single optical spectra per galaxy, you get these maps of optical spectra. And this, just for those who are not so familiar with optical spectra of galaxies, this is showing in red kind of the spectrum of a typical massive galaxy, your typical passive, not forming too many stars galaxy. The line is red, but also the spectrum is red, right? There's more flux at the red end. And then also this very characteristic dip at 4,000 angstroms. And it's characteristic of an old stellar population. And then the blue line here is our actually bluer spectrum, more flux at the blue end, and emission lines from ionized gas in this lower mass galaxy, one that would be typically star forming. So this is the kind of data or this is the kind of sample that you expect from MaNGA. This is a single plate's worth of the sort of angular scale that we get these resolved optical data. This is actually an image of the very first commissioning plate, so it's not quite representative of the sample. But this galaxy here was included as a kind of poster child galaxy. I guess it's Markarian 848, which has a HST image. So this is the SDSS image. HST is higher resolution optical image because it's in space, although it's a similar size telescope to the Sloan telescope, which is interesting. And then this is the kind of resolution we get through the MaNGA instrument. So this is looking at reconstructing an optical image through the MaNGA instrument. You see it's much more pixelated, but instead of just, 3 or a single color flux at each pixel has a full spectrum. So there's lots of physics we can do with this. So we get a lot of data per galaxy, all of these spatially resolved optical spectra per galaxy. We also get a lot of galaxies in the Sloan method. I think this visualization shows about half of the final sample in the background there, showing the G-band flux coming through the MaNGA bundle. And then I've also inset a couple of typical optical population charts here. So this is showing the I-band magnitude against near infrared minus R band color. So you can kind of make out the blue cloud and the red sequence here. This one is star formation rate, stellar mass. Again, those two populations of galaxies. They don't look quite as bimodal as you might be used to because of the way the MaNGA sample selection was put together to kind of be representative of the galaxy population. So sort of filling in some underrepresented areas. It's a beautifully designed sample selection, actually. You can read about it in Wake et al. 2017. So yeah, so lots and lots of galaxies and lots of data. So this is going to flick through the same galaxies, but showing you different slices out of the optical spectroscopy. So we get H-alpha flux for every single galaxy, which is tracing the ionized hydrogen, either from star formation or AGN or other ionization processes. I mentioned that break at 4,000 angstroms. If this is high, you can tell you have old stars primarily in your galaxy. So this is showing the maps of that feature across galaxies. There are emission lines and absorption features. So we get also velocities, and you get velocities from stars and gas separately, because absorption features from the stars, emission lines from the gas. So enormous amount of data per galaxy from the MaNGA galaxy, from the MaNGA survey. And MaNGA's goal was to kind of, and continues to be, to reconstruct the life history of galaxies with this statistical sample. So look at things which probe the birth, growth, and death of galaxies. And so these are some of the questions that were in the original proposal for the MaNGA survey. how does gas accretion drive growth? What quenches star formation? How is angular momentum distributed? And how do various galaxy components assemble and influence each other? And one of the things you might notice is how much these are heavily linked to the gas content of the galaxy. So optical spectra can probe stars beautifully, also the ionized gas, but without playing a lot of games, are completely insensitive to the cold gas content of galaxies, or playing some interesting games. So we built the HI-MaNGA survey, the follow-up, we built it on the MaNGA key questions and talking about how having access to the total H1 content and also H1 rotation widths of as many of the MaNGA galaxies as we could observe, how that would really add to the survey. And because the strength of MaNGA was really in its numbers, we wanted to try to match that with H1 data, which we have been able to do thanks to Green Bank observing. So why is Green Bank ideal for this? Or why was it, I guess? So I already showed you the picture of the Sloan telescope. This is located in New Mexico. It's at Apache Point Observatory in New Mexico, so sort of mid-latitudes of the US. And the way the MaNGA survey was built was to target the galaxies which met the criteria across the entire footprint that was imaged by the first phase of Sloan. And so the gray here shows you that. So the gray here shows you circles inside which each would have 17 MaNGA galaxies that is somewhere in the Sloan imaging footprint. And actually not just Sloan imaging, it's actually Sloan imaging plus that redshift survey, the 1 million galaxy redshift survey. But unfortunately, despite getting lots of telescope time at Apache Point, we didn't have enough to do every single galaxy that met that criteria in the footprint. So we just randomly selected them. And the observing script was designed as to it had a few priorities to do with overlap with ancillary data, but primarily it was designed to be as efficient as possible. And if you are in a telescope that's at 30 degrees latitude, the most efficient things to look at are going to be kind of high in the sky when you're at 30 degrees latitude. And it just turned out that it tended to be the case that things between about 30 and 60 degrees latitude declination were the most efficient to observe. And so that's where a lot of the MaNGA sample is. And that's what the purple circles here are. This is actually the final survey footprint. Observations are all done. This is what it ended up looking like. So if you've been paying attention, you notice that that is north of where Arecibo could observe. And so it is, or a lot of it is. So a lot of it is north of where that untargeted alfalfa survey is. So alfalfa is great for the things which overlap in MaNGA. There's really no need to do anything more than alfalfa in those parts of the sky. But for a big chunk of the MaNGA survey, there was no existing H1 data and not really any significant plan that it would just happen naturally going forward, at least back in 2014. There was this the Apache survey, and this is an older and slightly busy sky map showing different kinds of surveys overlapping on the MaNGA footprint. You can tell it's older because not all of it's been observed yet in this version. But you can see where alfalfa is. I've also put UKIDS here in the brown. And you can see MaNGA did favor a little bit areas of the sky that UKIDS overlapped. HSC imaging. It also shows the footprints of the SAMI survey, which is the similar Australian IFE survey. But looking at things like this made me think that Green Bank would be an ideal telescope to do H1 follow-up for the MaNGA survey. Of course, one of the most common pieces of feedback that I get about the H1-MaNGA survey is, wouldn't it be nice though to have it with the same spatial resolution as MaNGA? I mean, that's what you'd really like in an ideal world. If I had a magical telescope, that's what I would get. I would get H1 data with the same spatial resolution as the optical data in MaNGA. But it's just not really feasible. We already talked about how if you're using Green Bank, the scale of the area that you're sensitive to, the single pixel that you have access to with Green Bank at 21 centimeters is much, much larger than a typical MaNGA galaxy. But we know what the redshifts are. We have optical redshifts for 100% of the MaNGA sample. We even have rotation for most of them. We kind of did a lot of the H1 observing in parallel with the optical observing. So sometimes we observed in H1 a little bit before we had access to the rotation. And so it's very easy to uniquely link the 21 centimeter line emission to the optical galaxy, or at least to know that there might be some confusion. And so you'll see we do include confusion flags in what we put out publicly. Why am I so adamant that it's not feasible to get resolved data? And this is actually a slide that I mostly use to convince my optical colleagues of this. And so this gives a sense of the typical time per galaxy to get useful H1 data from various facilities. So the GBT, this 15 minutes on off is what we chose to do with the HI-MaNGA program in order to match roughly the sensitivity of the alfalfa survey. So alfalfa runs Arecibo, was obviously much bigger and was a drift scan model. If I've got the numbers right, it was 40 second per beam integration with that drift scan at 3 arc-minute resolution. We can get similar sensitivity at Green Bank, actually just a little bit better with 15-minute on-off. So 5 minutes on, 5 minutes off, and 3 pairs of those, which takes about 35 minutes of telescope time. And you get 9 arc-minute resolution, which is not what you'd like, but is what you get. If you wanted to do better, if you went to the VLA, you might hope to get something on the order of arc-second resolution, the beautiful things data. Oh, I didn't say this, but the MaNGA spatial resolution is about 2 arc-seconds through those fibers. So this is still not quite matching the MaNGA spatial resolution, but to do this would be tens of hours actually per galaxy, most likely. So it's just not going to be feasible with the VLA anytime soon. And Apache is doing that small area of MaNGA, and we'll have higher resolution data in that small area on the order of 30 arc-seconds. So actually about the size of the bundle will be the resolution element from Apache, and it would take on the order of hours per galaxy. But we don't get, as I was trying to say, I feel like I'm disparaging single dish 21 centimeter line observing, which I'm not at all trying to do here. We get a lot of useful information from the single dish observing. We get the integrated flux tells us the H1 mass because we know the distance. That we get a spread of emission caused by the rotation. We even get a little bit of information, I argue, about the radial distribution from the shape of the profile. Like a little bit hard to disentangle, but we have full velocity maps for every galaxy, at least in the central part, through MaNGA. So I think there's some hope of using those two pieces of information together to get a little bit of information about the radial distribution of H1 in these galaxies too. So we have proposed across many semesters. I was the PI of the initial ones, and then Dave Stark joined me as a co-PI later on. And we've actually observed about 2,500 hours on Green Bank for this program. That has allowed us to get data for over 4,000 of the MaNGA sample at this 36-minute per galaxy type observing. And then we add to that about 2,800 from alfalfa, from the beautiful alfalfa survey, which, if you can do that sum in your head, adds up to about 70% of the MaNGA sample now with H1 information added. So how did we do 2,500 hours of Green Bank observing between mostly the two of us over a few years? And I'm going to tell you actually the 460 hours that I did as a postdoc remotely. That was a lot of work sometimes. That was a lot of staying up late, working to do remote observing. It would not have been possible to do this if we had not gotten permission for an automated program. And big thank you to the operators who've run our program over this last several years. And a big thank you to Dave, actually, who wrote this observing script. So we have an automated observing script that runs in Python. So it runs through Astrid. It looks at where Green Bank is looking at the time that we get control of the telescope. It looks at our catalogs and decides which is the best target to move to minimize overhead, minimize the slew. It then will run the calibrations, and when the observing is done, it also updates the observing catalog, so there's no risk of re-observing the same galaxy should it run again before we have a chance to look at it. We also implemented a way of prioritizing targets. If there were certain galaxies we were really keen to get data on quickly, we're able to kind of bump them up the priority list. And what would happen is this script would be run by one of the wonderful operators. And then after it was done, during normal working hours, either Dave or I would check over the data, check that the catalog updates work well, and make sure everything's running smoothly for the next time we got time on the telescope. almost all of this was run as a filler program, and having, I think, the automated script has meant that they've been able to use much shorter periods of open telescope time than we might have otherwise. And so that's how we've managed to get so much Green Bank time for this program. The other thing to shout out to is how beautifully well behaved and stable Green Bank is. We took calibration data every observing session for H1-MaNGA, and so this is showing you the calibration temperatures from those data processed by a student here at Haverford, and we published it as a research note. And you can see how the calibration remains really impressively stable over this 4-year period, although it is about 20% offset from what's in the data reduction pipeline, which is provided with caveats that it might not be correct, so that's fine. So that was nice to see. The other thing we've implemented that makes this possible is trying to get students involved in the data reduction. So again, big shout out to Dave for spearheading this effort to make a pipeline that is designed with people who don't know very much about radio astronomy in mind. And so we have this wrapper that runs within GBT-IDL that students do not need to learn any IDL. And we actually, thank you again for letting them all have accounts. We also don't even have to get them to install IDL or have licenses. They all get accounts at Green Bank, and they run this. We teach them how to run this script, and then they go do the numbers in order and do the different steps. So that's been beautiful. It's really worked out as a beautiful entry point for undergrads to get involved in research. So we've had, I think, 20 or so different undergrads help with this data reduction over the past few years. So I think this is a screen grab of Dave and me having a Zoom meeting about data reduction with some of the students. I think it was actually 2 summers ago. So, they learn about radio astronomy and we get a little bit of a boost to the data reduction. So we're not quite done actually with all of the data reduction, but we're getting pretty close now. So hopefully we'll be able to have a final data release for the program pretty soon. Yeah, so we've observed about 7,000 galaxies in total across the Green Bank data, and then filling in with alfalfa in that part of the sky. So that's been really cool. That's about 70% of MaNGA. Because we're a Sloan project, we also committed to public data releases. So it actually, the most recent one went out with the Sloan DR17, which happened last December. We put out almost all of the data, 6,632. We've made a homogenized catalog, so it doesn't matter, you just get the best H1 mass and width in the catalog. Dave also worked pretty hard on getting optical counterparts and characterizing the potential for confusion within the 9-arc minute beam. And so that's all available in the catalog. And you can also access the spectra. So reduced and baseline subtracted spectra are up in the database. So there's various ways to access this as well, since it's in the Sloan infrastructure, including accessing it through Marvin, which is the Python package, which lets you interact with MaNGA. So it's hopefully something that lots and lots of people will be able to use for many years to come. So just a little overview of what the sample looks like. This is the DR2 sample. I'll just skip ahead because I want to make sure to tell you a little bit about science and also not go too much longer. So this is a really nice piece of work that Dave did. This is the Stark et al. 2021. So it was based on the second data release we did. And Dave was looking for what correlates best with the H1 mass, here characterized as the log of the H1 mass divided by the stellar mass. So this is plotting that for the whole H1-MaNGA sample we had at the time against the equivalent width of H alpha. And then here against the average specific star formation rate within 32 million years from population modeling. The equivalent width of H alpha is a bit like the specific star formation rate, right? Because the H alpha flux comes from star formation, and then the continuum, the thing that you're calibrating it to get to be equivalent width, is coming from stars. So this is like very short time scale for star formation, and this is a much longer time scale for star formation. So you can see there's a much stronger correlation of H1 content with star formation rate averaged over a long time scale, and a very weak correlation with recent star formation, which we know. We know that molecular hydrogen correlates much better with recent star formation. But it's kind of neat to see that if you look at it over longer time averages, atomic hydrogen has a better correlation. So here is this implication that this is showing how the atomic hydrogen is sustaining star formation in these galaxies. Here's another neat one. So this is the hydrogen gas mass. So this is in log of solar masses on the y-axis here, plotted against the star formation rate, log of the star formation rate. So diagonal lines in both of these plots show the depletion time. So how long that mass of hydrogen can sustain that rate of star formation before you run out of fuel. And then the points are color-coded by these two different parameters. This is the ratio of oxygen to H alpha line, which has to do with shock heating. And then this is the surface brightness of H alpha, so how dense the hot gas is, I guess. And you can see that the depletion time depends on both of these parameters, which kind of makes sense, actually. We're seeing longer depletion times where the gas is more diffuse and perhaps has more shock heating, so it's less able to collapse and into molecular hydrogen and form stars. We have a big sample, so we can find weird galaxies. So this has been a fun project with Anubhav Sharma, who's a computer science major about to graduate this year from Haverford. We basically looked at the galaxies that have very large H1 masses, but don't appear to be actively star forming at all. And what it looks to be is that it's kind of a diverse sample, actually, but one of the things that we keep coming back to is this idea that they seem to be characteristic of minor mergers. There's something going on which is exciting the kinematics a bit, so they tend to have a little bit higher velocity dispersions and rotation speed. And they also have a high fraction of counter rotation. So where we see that the H alpha, the ionized gas, is going the opposite direction as the stars in the MaNGA data. So this is really neat. We're just working on the referee report for this, so hopefully it will be published quite soon. So there's been tons of student projects that we've been able to run with the H1 data, and many more to come, I'm sure. I think in the interest of time, I'm just going to skip ahead to the end and just say thank you very much to Green Bank, particularly the operators, for running the H1-MaNGA program over so many years. I think I will end here.
All right, beautiful. Thank you very much, Karen.
Sure.
At this time, I'd like to turn it over to the audience. If you have any questions, feel free to raise your hand and I can unmute you. Or if you wish, you can ask a question in the chat. So I think first there are a few questions here from the Q&A that I'll go through. The first was at the very beginning of your talk, which was asked, where can I access the GBT image of your first slide?
Well, that's a good question, isn't it? And despite the fact that saying I hadn't given this talk many times, I will admit that it was just a picture of the Green Bank telescope that I had in a talk already. And I don't know is the answer, but I can get back to you.
Yeah, and I don't know if that particular image.
That's one I took myself. It's plausible, but I don't actually remember that it is. And it's very bad of me not to put credit. So my apologies to whoever took it if it's not me.
Yes,
but I'll
but
write down who asked it, and I will look it up and get back to you.
Yeah, but you can find a great many photos, both historical and more recent, on the Green Bank Observatory Flickr page. So you can also go looking there for a lot of great images.
Awesome.
And then we have a question, is GBT sufficiently sensitive to observe similar to the H1 transition in deuterium?
Yeah, so I'm gonna follow my own advice to students here and just admit I don't know the answer to that. I don't know if there's any experts in the audience who know the answer, but I do not know the answer. I think possibly not. It's a lot fainter, if I remember correctly. But I don't know for sure.
All right, let's turn to an audience member, David Blank. Feel free to talk.
We don't hear you if you're talking, David.
You'll have to unmute yourself first. All right, well, he's figuring things out. We have another question from Jim Jackson saying...
Sorry, I was not listening. Approximately what percentage of your detection limit was near, considering it low redshifts to higher redshifts? Because for 35 minutes, I think that when you're talking about Z of, 0.0405, it must have been fairly low.
Yeah, so let's see. So this here is a diagram that shows you the atomic hydrogen mass that we calculate from the data as a function of redshift, and then we can also estimate the upper limits. So I didn't emphasize this though. We have a detection fraction in HI-MaNGA about 60% actually. So about 30 to 40% of the time we don't detect what we're looking at, but it's not useless. That gives you an upper limit as to the H1 mass that could be in the galaxy, and with proper statistics. And if you want to read about such statistics, I refer you to the appendix of Dave's paper. The references here, and other places too, but we're quite careful learning about survival analysis for this work. With proper statistics, you can make use of upper limits. So yes, indeed, at the highest redshifts, we have a lot of upper limits.
All right. Okay. If one had any idea for student projects, one could just email you.
Sure. Yeah.
Okay. Thank you.
Sure.
All right. Brilliant. So yeah, we next have a question from Jim Jackson, the GBO director himself. So this has some weight behind it. If you could have any new capability on the GBT to support this kind of work, what would you want?
Well, multi-beam receiver would be really lovely. And because that would mean that instead of 5 minutes on, 5 minutes off, we could make use of all the time for an on. So with a multi-beam receiver, if it's designed nicely, you can use like a different, you can kind of, if you, you could put on and off in the same, I'm not explaining myself, I'm sorry, Jim knows what I'm talking about. I think that's why I'm like flailing around with my explanation. But you move so that your off position has your galaxy as an on in a different beam, if that makes sense. And so you can basically make use of 100% of the time. So we could do the survey twice as quickly, and it was pretty quick already. That would be really nice. Yeah. Well,
You'll have to work and see if such a dream can come true.
Yeah.
We have another question from the chat. Have the observations also included dwarf galaxies?
Yeah, so let's see. So the MaNGA sample itself doesn't have many dwarf galaxies, but it does have a few, and it has, in particular, it has some additional targets, so not core sample targets that were aimed at dwarf galaxies. And what we did for target selection for H1-MaNGA was literally anything that had been observed by MaNGA already. And I would get the latest, off the telescope, these data have been observed, even if they hadn't been reduced yet from MaNGA. We would target anything within 0.05, redshift 0.05. You can see the cutoff here in this chart. And that cutoff was selected partly because of the San Juan radar. So that's a bit of a weird thing to say, but so in Arecibo, there's a little bit of dip in sensitivity between 0.05 and 0.05 something that's caused by the fact that you can't observe when the San Juan airport radar is on at the same time, or couldn't, I guess now, none of it's working, but anyway. And so there was a dip in sensitivity to galaxies there. And we just thought, looking at the MaNGA sample selection, it kind of made sense to just stop at that 0.05. That was also where, uncomfortably large fraction of the galaxies started to become upper limits instead of detections. MaNGA, the way the sample's designed in MaNGA, the more massive galaxies are further away, so that helps a bit, because even though the more massive galaxies like proportionally have less H1, they're still more massive, so they still actually have more H1. And so, they're a little bit easier to detect. So we don't have as big of a trend of detection fraction with redshift as you might get in a random sample, because of just some of the weird oddities of the way the sample's put together.
All right, we're at the hour now, but we have one more question in the Q&A. So would the fast beam better correlate with the MaNGA resolution?
I mean, it's closer to it, sure, because fast is more Arecibo sized. So the beam, I believe it's even a little bit bigger than Arecibo, right? So the beam's got to be less than 3 arc minutes, but it's not going to be 2 arc seconds, because that's a factor of 60. So sure, it's better, but it's still much, much, much bigger than MaNGA spatial resolution.
All right, brilliant. So unless there is one final question, either in the chat or someone wishes to raise their hand. If not, then I wish to give Karen one final thank you for joining us today and talking about this topic. And thank you as well to all of our attendees for joining us in our first in our colloquium series. A quick reminder to please join us next week for a talk on the history of pulsar discoveries at the Green Bank Observatory, given by Dr. Maura McLaughlin. So thank you very much and have a great rest of your day.